I understand some groups are confused. All right, let's see if anybody have something they would like to share with the class. Your best guess, anyway. Please understand it might be wrong. If it's wrong, we'll talk about it. So does anybody have a whiteboard that we can share and then discuss? Okay. Nobody's saying anything. So I'm going to, okay, same here. I think we all need some pointers. Okay. All right. Well, I'm not hearing anybody say anything. So let me ask you some questions here. Ooh, we have a volunteer. So I'm going to switch it over to Eli, I think. And keep in mind, keep in mind if it's wrong, that's all right. We'll talk about it. All right. So Eli. Okay. So what you guys is thinking, Eli? Can you?
Can you guys hear me?
Yep, we can.
Or, so what we were thinking is that B on the inner side it has no charge, and on the outside it has Q.
Okay, and then you got a question mark there.
Yeah, because we weren't sure.
Okay, so can I ask you some impressive? Hey, it's impressive that we're willing to try. Okay, so what's your thinking? How did you come about with the no charge on part B there? What are you thinking there? How did you get that?
I was just thinking from the stuff that we talked about yesterday, how usually it's not on the inside and it all goes to the outside.
Gotcha. So you were thinking about the E fields, right? The E field lines.
Yeah.
Gotcha. Okay. Let me go ahead and take the control back from you, and I appreciate you guys willing to contribute. Okay. So.
Yeah.
All right. Okay. So this one was I had thought it was going to be. So let me see if I can give you some ideas and give you to think about something, and then maybe let you go back at it again here in a second. Okay. So if I can draw something here. Let's say that we've got this metal ball and that it's neutral. Let me draw something else on it here. It's on the stand. It's on an insulating stand. So this is metal here. And we have another ball here that's touching it. Ooh, wonder if I can move this. What happened to it? I think, oh, all right, let me try. Oh,
I think you need the select tool.
Thank you. So I've got these things and touching it, and I'm going to bring up a rod near this. And let's say this rod has a bunch of positive charges on it. So it's kind of like one of those rods we had in class, you know, those hard rubber rods that you could kind of charge up. And these are two metal balls that are uncharged, so they're neutral to start off with. So here, actually, let me erase it. So let's say this isn't here. If they're neutral, tell me something about the charges. Are there charges on these balls? Are there any charges in there? Yes or no? Say something. Yeah, there are charges, right? How does the number of positive charges compare to the number of negative charges? Same. Okay, good. All right, so now I'm going to bring up that rod again that's charged up positively. Okay, now we know metal balls, or any type of metal, conductors, charges are free to move, right? Say something. Yes. Okay. So we know there are charges in here. If I bring this positive near it, what will happen to the positives that are in this ball here close to this? They'll go away, right? So if this ball here is A and this ball here is B, where will those positive charges tend to go? To B. Okay, so therefore this is going to be positive. And then what will be the overall charge of A then? Negative, right? Okay, the negatives are going to be attracted to it. Now, if all of a sudden I were to get rid of the rod, what would happen to these charges, the plus and minus? They'd equalize, right? They'd go back to being, so they'd move back around, right? And they'd be canceling one another out. Let's say, though, while the rod is still here and it's positive charged, let's say that now I separate out these balls here, okay? So separate the balls out, and then I remove the rod. What would be the overall charge of A? Negative. What would be the overall charge of B? Positive. Okay. So now what's the connection here? Okay, here's the connection. Keep in mind in this problem that this insulator in the middle had a charge that's positive. Also keep in mind that this neutral metal is surrounding it. Think about this surface here is a lot closer than the far surface, okay? Why don't you go back in your whiteboarding groups and see if you can come up with what the answer is to the inner and outer surface. Any groups need more time to think about this before they make their guess? If so, say something or type something. Okay, I'm going to, since I didn't hear anything about needing more time, I'm going to go back to Eli's group since they were nice enough to, or brave enough, I should say, to actually venture out there with a guess. And I'm going to go back to them to see if they've changed their answers at all. So let me see if I could pass it over to Eli. Okay, so Eli, you've got talk?
So yeah, the
So what are you
question
thinking?
marks. You can
Oh,
kind of see from our chat that we're not really sure if
not
it should
total.
be.
You're not totally 100% sure, but let's see what you said. You said for part B, the inner surface would be negative. And the thinking about that is that you have a positive in the middle, and what's going to be attracted to that positive?
The negative.
Negative, right? And so that makes sense. So what's going to be on the outside then? What's being pushed away from that positive charge that's in the center?
The positive.
The positive. Now let's use one more piece of logic to see if this makes you feel a little bit more comfortable about your answers. If you add up the surface charge on the inside of the metal and on the outside of the metal, what do you get? If you add the
equal 0.
Yeah, it should, right? It should be 0. If it started out neutral, it has to end neutral, and it does, doesn't it? So how do you feel about your answers? Do you feel a little bit more confident about your answers?
Yeah.
Yeah, I agree with you. And it looks to me like, based on the chat for everybody else and join me, it looks to me like they agree too, and I agree. So we're going to keep that as the answer. Any questions from anybody?
Ben has a question, it appears.
Ben, okay. Okay, so let me take control so that Ben can talk then.
Hello?
Yes, Ben, go ahead.
matter how far away that outer sphere is, its inner surface is going to have a charge of negative q, and its outer surface
Yeah,
is going to have a charge of q.
right. Only if, though, here's the thing. Only if the outer shell, or the shell that you're talking about, is a conductor. If it's an insulator, those charges can't move. They're stuck where they are. Now, true that the molecules themselves can get polarized. What that means is they rotate, but still the overall charge of the inner surface is going to be neutral for an insulator. Now, for a conductor, though, they can move, and yeah, no matter how far away, the inner surface is going to be the opposite charge then.
Okay.
Okay. And actually, Eli, I'm not sure if Eli can hear me here, but Eli was thinking something about the electric fields inside of a metal, and the electric field was 0 inside the metal. And this is going to be why it's important that we have to do this, because Eli's earlier insight about the electric field. Okay. So any other questions? And you'll see here in a second. Any other questions? Okay, I'm not seeing any questions. So now what we're going to do is we're getting ready to do part D, where it says write down the electric field at space using Gauss's law. Okay, so you're going to be using Gauss's law, which, just to remind you, says that the electric flux is given by two statements. It's the sum of E dot dA that's the electric flux, the electric flux, which is also equal to the Q enclosed divided by epsilon naught. Okay. Keep in mind this is Q enclosed. Let's see if I can put ENC here. Okay. So what I want to do is we have several different spots. We have to do it all points of space. So I want to start from way outside. In other words, R, little r, is going to be much bigger than 3r. I want to start out here. Okay. Since this is the first time where you're actually trying these problems, I'm going to kind of help you guys out a little bit. So what's the first thing I have to do? I have to draw something. Somebody help me out. Type it in or say it. A circle. Gaussian pillbox. There you go. So I'm going to draw a Gaussian pillbox that mirrors, not a free body, no. I'm going to draw a Gaussian pillbox that mirrors the charge distribution. Okay, what kind of will this pillbox have? A sphere, that's right, not a circle, a sphere. So I'm drawing the cross section, which looks like a circle, but it's actually a sphere. Oops, that's not a good one. So sorry about this, but imagine. Okay. Now imagine a section here, a little tiny section. The E field. Remember, you guys said that there was a negative charge on the inner surface. And you said that there would be a positive Q on the outer surface. So we have this E field, because it's a positive Q. Sorry, that should be perpendicular there, sorry. That's the E field pointing out. And we're going to have an A vector that's also pointing out. So the side that looks like it's hard, the calculus side, that's going to be easy actually, because the E field's constant. Any questions why the E field's constant? Nope, don't see any questions. So on that side, it's going to be E. And then we're going to sum up the area. What would the area of my pillbox be? So let me type it in or say it. It's not 4 pi r cubed. What would that be? What's 4 pi r cubed, or 4/3 pi r cubed? What's that going to be? That's not right. Okay, so he's apologizing for that. That's volume, that's right. We don't want volume, we want the surface area, which is going to be 4 pi r squared. Okay, that's going to be equal to Q enclosed, and this is where I also need some of your help. Okay, there's lots of Q's enclosed, so I have to do the entire amount of Q enclosed. I have a positive Q out here, I have a negative Q in here, I have another positive Q in here. So how much charge is enclosed total? Okay, keep going. I want to hear everybody say it. I see a lot of, there you go. It's positive Q, right? Positive big Q. Okay, divided by epsilon naught. Okay, so any questions about that? Okay, of course I could solve this now for the E field, and the E field is going to be equal to Q over 4 pi epsilon naught 1 over r squared. Okay, so it's an inverse relationship. Michael, that's a good question. What is this little r I'm talking about? Here, let me draw it. I want you to see, because that's a very important question. It's little r is different than big R. That's right. It's very confusing for students. Big R is this R. Big 2R is this R. Big 3R is this R. Little r is always to the Gaussian surface. This is little r. Okay, so that's very important. Okay, now what you're getting ready to do now is, so I've done kind of the first one for you. That's for all points outside. Okay, the next part that I want you to do, and again, it's only one part, is I want you to do where little r is bigger than 2r, 2 big R, I should say. But I want you to do it where little r is less than 3 big R. Okay, so where am I talking about? I'm talking about inside of the metal. So you're going to be drawing a Gaussian pillbox inside the metal. You're going to be doing this same equation. Okay, no, I don't want you to say any answers. I want you to work it out and see why. Okay, so go ahead and get in your whiteboarding group and start working. I think you're breaking, Mike. I'm not sure if you're trying to talk. Yeah, okay. Okay, is anybody willing to present and kind of explain to me how they get their answers, or explain to the whole group anyway?
I didn't write anything down, but I can explain it.
Okay, so I will pass you, and
Well, I can just explain it over the microphone because I didn't put anything down.
not even on, well, you know what? Even when you're talking, I'd like you to be able to draw, so I'm going to pass it to you anyway.
Okay.
That way, Mike, if you need to, you can draw and you can kind of explain why it is what it is.
Anyway, the enclosed area would be between these two shells. So if you've got plus Q and minus Q in there, then it adds to 0. That's
Okay.
enclosed.
So you're saying when you draw a Gaussian pillbox between those two dotted circles you just drew, the amount of charge enclosed would be on the inner surface would be negative Q, and on the inside inside insulator was positive Q, and so therefore the net charge is 0. Is that what I'm hearing from you?
Yeah.
Okay. Anybody have any questions? Okay, I'm going to go ahead and take control. Thank you very much. Appreciate it. Okay, so now what I want you to do is, I think you guys can hear me, is now what I want you to do is draw your calcium pillbox in here, in between R and 2R. So now you're going to do where little r is bigger than but it's less than 2r. Okay, too big R, I should say. Okay, so again, you're applying Gauss's law, which is going to be closed integral of E dot dA is equal to Q enclosed over epsilon naught. Okay, so go ahead and get in your whiteboarding groups and work on this problem. Can anybody present? Does anybody need more time? I'm assuming, if I don't hear anything, I'm assuming you guys don't need more time and I can just pick somebody at random. Okay, so Kurt, Mark's in your group. Can I pass it to Mark and he can talk? Oh, and Mark's not in your group. I'm sorry. Oh, that's right. Michael's in your group, but he's already, has Michael already presented, didn't he? Okay. Well, I think I'm going to switch it over to Kurt then, and we can at least look at his. Okay, so but you can at least hear me, and he's got Gauss's law, and he found out the E field was constant, so therefore he summed up the area and he got 4 pi r squared, and that was the little r. And so the Q enclosed would just been the positive Q. And so really this equation looks exactly like it did for figuring out outside of contraption. So Kurt, did I do okay explaining it? Okay, all right, so any questions? Okay, so we're getting ready to do the hardest one. I'm going to go ahead and take control back away. All right, so first of all, I need to come down here at 24 through 20 because this is what we do next time we get regardless. 24 through 7, the only way this is different is that here we have an insulating ring around. So here we have the same thing, positive Q in here, but now instead of being a metal conductor, we have an insulating ring. So that's the only thing that's going to be different. So in a lot of ways, this one's going to be exactly the same up above, or maybe easier. So just think about that. We're getting ready to do the hardest part here. And the hardest part is we're going to be, I need to change my color. We're going to be inside. So we're going to be drawing a Gaussian surface in here. Keep in mind that this is an insulator inside of here. Okay. So we're getting ready to do where R, little r, is less than big R. Now this doesn't change. This is totally true. And really the left-hand side, which looks at first like the hardest side, is actually the easiest because can you see it's going to be the same pretty much every time? Any questions about why it looks the same? Okay. It's because that geometry is the same. So that's left-hand side doesn't change. The thing that's going to be hard is the right-hand side, and really the hard part is figuring out Q. Will all the charge, all the positive Q be inside of the dotted red line there? Nope, right? How will you figure out how it goes in the dotted red line? Using, well, okay, well, actually, since they give us Q, usually you do, Kurt, usually you will have to use the density because they won't give you how much charge it is, but they'll give you the density. They'll give you rho. But since we know how much is the entire amount here, we don't have to use the density. Yes, fraction, okay. Michael, go on there. A proportional fraction of what? Oh, Mike, yes, I see Mike. Volume fraction, right? So the amount of charge, this Q over epsilon naught, that doesn't change, but I'm going to have to multiply it by a fraction of the volume. Well, the volume of the whole is going to be, hey, how do you find the volume of a sphere? Somebody write it in. Kurt, actually, Kurt, let's see what you got. What's the volume of a sphere? There you go, right? 4/3 pi, and it's not going to be little r, it's going to be big R cubed because it's the entire sphere here. And on top, it's going to be the Gaussian pillbox, which is still going to be a sphere. 4/3 pi. But what is this going to be here? Big R or little r? What is it going to be? Little r, that's right. Little r cubed. So I actually helped you out quite a bit here, okay? I would like you to solve it for E. I've kind of worked out this side over here, and I've left you the easy side. So go back in your whiteboarding groups and solve for E. This will be the way. Can anybody present? Quicker we get a presentation, the quicker we can sign off and leave. Can I have, as Michael called it? Anybody out there? Need more time? Do you need more time? Is that the problem? I don't think that's a problem. Okay. Oh boy. I think they're afraid. Okay, Ben thinks he has it. So I'm going to go ahead and flip it over to Ben. Let's see, here we go. Okay, and Ben, if you can go ahead and take over.
Can you guys hear me?
Yep.
All right. So we have the equation that you got for us. We simplified a little bit, got rid of the 4 pi on both sides of the fraction. And then all we did was find dA. We got was 4 pi r squared divided by that. Cancel out the 2 r's on the bottom and 3 on the top to get, and 2 on the top to get qr on the top, and then just over that.
A question, Ben. The other ones were inverse square relationships. What will this one be if you were to graph it?
This one would be
And I should,
the r.
yeah, let me clarify a little bit. I should have said if you graph E versus little r, what kind of relationship would that be? I'm sorry.
Just linear because you have the r on top instead of r squared.
Right, and so that would be a yeah. You're cutting out on me. I'm not sure what's going on. So yeah, that would be a linear relationship. So I'm going to go ahead and take controls. Thank you very much. Appreciate it. Okay, so just before I let you go, I just want you to understand that I expect you to have This one down, 24 through 27, the answers are going to be the exact same as up above, or since this is an insulator, it might actually be a little bit easier. Okay, so some of the answers might be a little bit different, but they will be easier because this is neutral insulator here. Okay, all that on side, this one in here, just like what we had before. Okay. I would also like to encourage you to start working on the E-fields and flux. This one's pretty tough. I think I would do that one actually last, and the other one should be pretty simple. You might want to think about the graph for this if you were to plot E-field versus the R, little r, I should say. That really we have some pretty distinct zones here. We have a big R, we have a 2R, and we have a 3R. And you really should start thinking about what this graph would look like, right? Okay, anybody have any questions? There's a question. Do we have this worksheet in physical form? Are you talking about down here, E-fields and flux? Which one? What are you asking me? No, the first, oh, this up here? Yeah, this one is actually the back. So it's the back side. Okay. Yeah, that's going to be due on Monday. Yeah. Or whenever we're back together. I'm a little bit Monday. And then this one down here, this is also. And again, if you left your packet at home, don't forget you can go back to My Big Campus. You can go to Current Agenda and Assignments. And then you can click on this packet here, and right there they are. Missy, if you missed anything, again, recording all this, and you'll be able to check it out later. Okay? Any other questions? Michael, if you missed it, I'm sorry. I'm making a video, so you'll be able to get the stuff anyway. Okay. Andrew, what did you say flux? What did you say flux is due Monday? I'm not sure I get that. Is that a joke? Okay, yeah, the lab is due the next time we get together. What I'd like you to do is start working on this flux worksheet next time we get together, whiteboard it. And I like to make the whiteboarding go a little bit faster. Okay, so any questions? We'll let you go. No? Okay, well, have a good e-learning day. I really appreciate your attendance. Oh, okay. Bye. If you have a question, just stay with me. Everybody else, goodbye. See ya. Thanks. Appreciate it. Okay, Raj, you had a question, so go ahead and say something or type it. I'm listening. Bye, everybody else.
4 through 27.
Say that again, Raj.
24 through 27, the second question for the worksheet. It says a solid insulating sphere in the center of the.
Yeah. Yeah, so Raj, up here, this center was for number that we just did, 17 through 23. It was also a solid center.
Does that mean that it has like a charge on its own?
Yeah, so just like in the previous one, this one in here will have a charge of positive Q that's distributed throughout it. So here's how it's different, Raj. It's actually an easier problem. If this is an insulator that's surrounding it, can you see? I'm not sure if you can see my cursor. Okay, so my question is, if that's an insulator, will there be just on the other one, if you remember, on the other one, on the inside of this, there was a negative Q because it was a metal. It was able to move those charges. It's an insulator now. Will there be a negative Q on the inside surface of this insulator?
No.
No, there won't be. Will there be a positive Q on the outside of this surface? No. So now, Raj, I'm not going to draw the whole thing, but imagine that you're drawing the Gaussian toolbox way out here, okay? Mm-hmm. How much charge is enclosed?
Positive Q.
Just positive Q, right? And let's say now all of a sudden I draw a Gaussian surface in here. How much charge is enclosed?
Positive Q.
Right. And how much, if I draw another Gaussian in here, let's say, how much charge is enclosed?
Same thing.
Yeah, it's positive Q, right? So how will the answer compare for all three of these Gaussian surfaces?
The same.
They're all the same, right? The only one that's going to be a little bit different is when you draw the Gaussian pillbox inside. But you've already done that up here. That's the one we just did. That's the very last one here. It's the same answer. Is that,
Well, I was just like, in the worksheets, insulating is italicized, so I was just wondering, like, what did that mean in context to the actual question? No.
so you're saying this word here, insulating, was italicized?
Yeah, on the worksheet, so it must have been important. So,
Yeah, maybe. Oh, yeah, you're right. I do see that. I think I was trying to call your attention to it because sometimes students will automatically think that the charges move. Well, they can't move if it's an insulator. Does that help?
yeah,
Did you have any other questions for me?
but not one of
Uh, I do.
Mike, yeah?
Oh.
Go ahead.
Yeah, can you just confirm what the final formula was for the little r is less than big R?
Oh, sure. In fact, let's go through that one. And I'll do it down here. So you would use Gauss's law. Whoops, that's a horrible. E dot dA.
Cubed over the big R cubed.
Oh, you just want me to tell it to you? You don't need me to explain it to you?
I think I can ask you if I don't get something.
Okay, yeah, I can just go ahead and tell it to you. The E field is equal to little r over the quantity 4 pi epsilon naught big R cubed.
Okay, times Q, right?
Yeah, I don't know if you heard me say that. Yeah, it was big Q times little r in the numerator.
Yeah, it must just cut out when you said that.
Yep.
All right,
So
that's what I
do you?
wrote down.
Okay, you don't need any explanation?
I think I got it.
Okay.
All
Any
right,
other
thanks.
questions? Yep. See ya.
bye.
Bye. Okay, Brooklyn. Okay, goodbye. Emily, I think you might still be here. Do you have any questions for me, Emily?